estimating the population mean. So last week we discussed confidence intervals. So we discussed them just in general, how to interpret them, how to interpret confidence levels, things like that. And then we talked specifically about how to do our confidence intervals for proportions. So given a proportion, we had a specific formula. Or we had a method in our calculator to calculate a confidence interval. And then we talked about how to interpret them and how to use them. So now we're going to do the same thing with means, but means are a little bit tricky. It's going to take us a little bit to get through them. This one section is going to take us the next 3 days because there's a lot to process here, and we're going to talk about why here in this first day. So when we're working with means, okay, our general form for confidence interval, you don't have to write this down. You've had this at least 3 or 4 different times throughout the notes. The general formula for a confidence interval for an unknown parameter, so for an unknown proportion or an unknown mean, you take the sample statistic. So what was your sample proportion or what was your sample mean? Plus or minus a critical value. What did critical values tell us? What was their purpose? Well, it was associated with the percent or the confidence level. So we found critical values based on the confidence level, but what did the value itself tell us? Like when I say 90% confidence, our critical value is 1.645. What does that 1.645 mean? Yeah, it's how many standard deviations we reach. Okay, so the critical value tells us how many standard deviations we want to reach in each direction. And then we calculate the standard deviation of the statistic, which we called standard error, because it was based on a sample value. So we had these 3 pieces. Now, when we deal with confidence intervals for means, we're going to have the same general formula. We're going to take a sample mean plus or minus a calculated critical value times the standard error for our mean. Okay? But when we work with means, things get a little more complicated. This was our formula for proportions. P hat, sample proportion, plus or minus Z star, times the standard error. Square root of P hat times Q hat over N. So when we dealt with proportions, it was really straightforward. We find those 3 pieces. All of them easy to find. P hat would have been given in the problem. Z star was an easy calculation. And then standard error. Very easy calculation. So, Z was used. When we talked about our critical value, we talked about Z because we had what type of distribution? A normal distribution. If our conditions were met, we could say that our distribution was approximately normal, which allowed us to use z-scores, which allowed us to use z for our critical value, how far we wanted to reach in each direction. Okay? Now, we would like to do the same thing for means. And again, don't write this down. We want to do this, because that would be very easy. If we follow the same idea, we would take the sample mean plus or minus our critical value z star times our standard deviation for our sampling distribution, which would be the population standard deviation divided by the square of the sample size. Okay? Now, what's the problem with this particular formula? Why can't we use this? So think about the pieces that we're looking at here. We won't know the population standard deviation. Remember, when we create a confidence interval, what's our ultimate goal? What is a confidence interval trying to accomplish? It's trying to capture the true mean. So when I create these confidence intervals, I'm trying to find the true mean, which means I don't know it. Now, if I don't know my true mean, I definitely don't know my true standard deviation. Now, this format, when we want to calculate a confidence interval, if for some reason, which will almost never ever happen, especially in the real world, if for some reason a problem would happen to give you population standard deviation. So if they give you sigma, then this is what you would use, because you have everything necessary to find what you need here. But like we said, we're never or almost never going to know the population value, because if we knew the population standard deviation, we probably already know the population mean, which means there's no point in finding our confidence interval in the first place. Okay? So if we know population standard deviation, great. But we're not going to deal with any problems that know that. Okay? So if we don't know mu, if we're going through the process of finding this confidence interval, it means we don't know mu, then we definitely don't know standard deviation. Okay? So, statisticians thought they had the perfect fix. Well, if we know we have a sample mean, which we have to calculate, that means we should also be able to calculate a sample standard deviation, right? So I can calculate x bar, I can calculate sx, that just comes from my sample. I calculated from my sample, this was the average height, this was the standard deviation of those heights. Okay? So, a very logical conclusion. Just replace population standard deviation with sample standard deviation. But again, something went wrong. So they used this for lots and lots of years. They started with the original and realized, well, that doesn't work because we don't know what the population value is. So they made this quick fix. And they were using this formula to calculate confidence intervals for means for quite a while. Until a Guinness beer taster. So there was a guy, his job was to take beer from the Guinness brewery. They send him a batch. He would test it out. So he would try it, make sure it tasted right, make sure that the ingredients were in the right proportion, make sure the acidity, everything about it was good to go. If anything was off, or if so much was off of it, he'd send the entire batch back and say this is a bad batch, and go from there. If it passed his test, then it moved on to the masses. Okay? But what was happening is, he noticed that as he was testing this, he was using this confidence interval for means, and he was using this formula. So he was saying, he was testing, if I'm using this batch, I'm going to create this interval. Does it capture the value that it needs to meet in order to pass this inspection? And what happened was, what they were doing is coming back. So everything he rejected, they tested the entire thing. So he was only taking a portion of it and testing it out. When he rejected those batches, they would test the entire thing. And what they would find is, when they tested the entire thing, everything was within specs. So everything was coming back normal. He was rejecting them, though, because of his sample values. And what he realized was he was making way too many mistakes. And it wasn't because he was doing anything wrong. He ran all the tests correctly. What he realized was their formula was wrong. The formula they were using to determine whether they wanted to reject or accept the batch was off. So what he did was, he took a couple years off, and he investigated the problem. And what he noticed was, we were using not only the wrong formula, we were using the entirely wrong distribution. When we looked at that formula, it was x bar plus or minus z times standard deviation, or standard error. It was assuming that we had a normal distribution. So what he did was, he went out and he started looking at things from a sampling distribution standpoint. Now, what the previous thoughts led to was that we should have a normal distribution. Okay? So he would take a batch, and he would take a look at it and say, okay, the population should be a normal distribution, the sample distribution. If I were to take sample after sample after sample and test it, it should follow this normal distribution, with the mean at the true population mean and with the standard deviation working itself out. Now what he noticed though was when he put a normal distribution, what it's supposed to look like, up on a graph, and then he overlaid his observations. So when he actually physically tested sample after sample after sample after sample, he created his own distribution and he laid it on top of this. And what he noticed was his distribution came out more like this. So logic said, this is what it should look like. This normal distribution, this mean with this standard deviation. And what he noticed was it looked more like this distribution. Way more area in the tails, way less area around the mean. So he recognized at that point that when we work with means, when we work with sample means, we're not even working with a normal distribution. We're working with something completely different. So he called it a t-distribution. So this is where you probably want to start writing some things down here. So when he standardized based on sample standard deviation, so when he was using the sample standard deviation to standardize results, our statistic created an entirely new distribution, which he called this, or the t-distribution. Sometimes in the book you'll see it referred to as students' t-distribution. So when he went and did the work here, he took on a pseudonym. He just called himself student. And so he created, or discovered, I should say, this distribution. So we're working with an entirely different distribution. We're no longer working with the normal distribution. Now we're working with a t-distribution. So this t-distribution has a slightly different shape than the standard normal curve. The difference isn't extremely vast. It's not like it's a huge altering difference. But it's enough that it was causing issues with their failure and acceptance rate. So it's still symmetric. It still has a single peak, the mean at 0. So the standard t-distribution, just like the standard normal distribution, when we're working specifically with z-scores, and in this case now t-scores, it's still going to be symmetric. It's still going to have a peak at 0. However, it's going to have more area in its tails. So what happens here is a t-distribution and a normal distribution lined up side by side from the same information. The normal distribution is going to be more compact. It's going to have less variability. It's also going to have more area towards the center. Whereas the t-distribution has more variability, values that fall farther away from the mean, and therefore then less area towards the middle. So very, very similar shapes. The only difference is more area at the tails, less area in the middle. Okay? So, like z, the value of t will tell us how many standard deviations x bar is from mu. So now instead of using a z star for our critical value, we're going to use a t star for our critical value. Now, something else he noticed as he was doing these calculations, as he was running through these different samples and these sampling distributions, and he was discovering this whole new distribution, he also noticed that if he changed the size of his sample, he changed the shape of his distribution. So when you think of the standard normal distribution, the standard normal distribution has one shape. It's bell curve, mean at 0, standard deviation of 1. There is no difference. It doesn't matter where the data comes from. If you standardize that data, it all fits the same curve. But what he noticed with this new distribution that he discovered is that if you change the sample size, it changes the distribution as well. Still has the same shape, still has that bell curve, still has the same center, but the variability changes as you change your sample size. So what ends up happening is we have an entire family of distribution. When we say the t-distribution, we're talking about an entire family of distributions that are defined by what we call degrees of freedom. And you're going to see that denoted as df. That's an important aspect of what we're going to be dealing with here. Now, your degrees of freedom are found by taking the sample size minus 1. So if you are working with a sample of 50, and you wanted to find your t-value, how many degrees of freedom would you be working with? So sample size was 50, how many degrees of freedom would you have? 49. So you would be dealing specifically with the t-distribution that has 49 degrees of freedom. If you change that to a sample of 30, you would have now 29 degrees of freedom, which means now you're working with a new t-distribution, one that has 29 degrees of freedom and so on. So every time you know your sample size, you know your degrees of freedom, which will give you a different t-distribution to work with. So when we talk about a t-distribution, you're normally going to see it with a subscript that denotes the degrees of freedom. So they'll either write, so if n equals 50, that means our degrees of freedom are 49. So they'll either just write T49, or sometimes you'll see them actually write out T and then df equals 49. So that subscript that comes with the t-value tells you how many degrees of freedom are associated with that particular distribution. With a normal distribution, we just call it z because there is no other distribution. It's just z. With t, we have to denote specifically which t distribution we want to work with. Okay, so these are going to be kind of the two notations that you'll see when working with t. Okay? So, we kind of illustrated it earlier. Here's just another way to kind of visualize what we're working with or what's happening here. So when you're comparing the t distribution to the normal distribution, t to z, several facts become apparent. First, the spread of the t distribution is a little bit bigger than the spread of the standard normal distribution. So when we look at this, the purple curve, so the curve, I'm going to put it in black here. This purple curve here is the normal distribution. Okay? Now, that's the normal distribution for a set of data. With that same given data, we can also create t-distributions. So the first one in red, the dotted line here, is a t-distribution with 2 degrees of freedom. So sample size of 3. So 3 degrees of freedom. Notice the difference. So between the black and the red here, more area out in the tails, more spread than the normal distribution. Okay? So that's one thing. The probabilities in the tails are higher in the t-distribution than they are in the z distribution, the normal distribution.
The degrees of freedom affect how you present just how it's described?
Yes.
So it makes it shorter?
So the fewer the degrees of freedom, the shorter it's going to be, and the wider the tails are going to be. Okay? Because notice when we go to the blue line and we look at 9 degrees of freedom, when we look at 9 degrees of freedom, notice we start to get more area in the center and we start to get less area in the tails. In fact, if I were to continue that progression, if I were to go to like 20 degrees of freedom, and then 40 degrees of freedom, and then 50, what's probably going to happen? eventually it's going to become a normal distribution. So the t distribution will eventually, given a large enough sample size, become essentially a normal distribution. But it's still going to have less area in the middle, more area out in the tails. So as the degrees of freedom increase, the t-curve starts to become more and more like the normal curve. So it's going to start acting more and more like that normal distribution. Now, the whole thing with this idea of confidence intervals and things like that with means is that in most cases, we're dealing with pretty small sample sizes. The guy who came up with this, when he was testing the batches for Guinness, okay, he was not testing really large batches. It wouldn't make sense. He's tasting them, he's drinking them, which means if he's trying to take a big sample, what's probably going to happen? He gets drunk, he's not going to know what the hell he's doing, right? So he had to take small batches. And because of those small batches, and notice what happens here, the smaller the sample size, the less like the normal curve you are. And that's why he started rejecting too many of those batches, is because his small sample size was a completely different distribution than the normal distribution he was basing all of his calculations on. So when you're working with this t-distribution, it's designed for very small sample sizes, ones that aren't going to get you to that normal distribution. Okay? So, finding critical values of t, finding t star, is a little bit different than finding z. So, the critical value, t star, that we should be used in constructing a confidence interval. If we want to find t star, two things have to be known. With z star, all we needed was the confidence level. That's all we cared about. Okay? If we knew the confidence level, we could plug it into inverse norm, we could plug it or look in the table, whatever we had to do, we find our z star. Okay? Or we memorize the common ones. Now, memorization isn't going to work with t because every single n gives you a completely different t. So for 95%, you would have an infinite number of t stars to memorize. For 90%, you'd have an infinite number of t stars to memorize. So that's not going to work for us. We have to be able to calculate these. So besides the confidence level, in this case 95%, we also have to have the sample size. Both of those things together will dictate which type or which t-star we want to utilize for our particular problem. So in your packets that I handed out to you, those formula sheets, go ahead and open up to, it should be called, I think, table B. So the first two tables you should come across will be your normal, and then you go to the next one, it's like table B, it says t distribution on it, it's like second to last page. Okay, so everyone get to that page. All right, so on that table, what we want to do is we need our sample size to calculate our degrees of freedom. Our t star is going to be based on how many degrees of freedom we're working with. So for our scenario, our degrees of freedom would be 11. So step number 1, on the left column, it goes through the different degrees of freedom the table gives you. So you would go down until you find 11. So find 11 degrees of freedom down on the left side. And then if you look at the very bottom of the table, it should give you confidence levels. Okay? So at the bottom, you have confidence levels that run across the bottom. So 50%, 60%, 80%, things like that. You're looking for 95%. So you go degrees of freedom for 11, go over to 95% for your confidence level, and where they meet will be your t star. So in this case, when we follow that up, we get a t star value of 2.201. Okay? Now, think about this as far as like a way to kind of check yourself on a test or quiz if you think you found the right T-star or not. Think about the Z-star or Z-star. If I were to find the Z-star for a 95% confidence level, what would it be? 2, or if we use the exact, would be 1.96, right? Now, since the T-star has more area in the tails, it would make sense that our T-value would be larger than our Z-value. Okay? So, if you calculate a T-score, or a T-star, I should say, and it's smaller than the corresponding Z-score, you did something wrong. Okay? You either used the wrong confidence level or something. Okay? So, your T-star should always be larger than what you would expect for Z. So in this case, 2.201. Now, the second option, if you don't want to use the table, is to use your calculator. Just like we did inverse norm on the calculator, your calculator also has inverse T.
Just space now, why do you pick the 2.5 or 0.05?
Don't pay attention to the top part. Pay attention to where at the bottom, it gives you your confidence level.
Oh, okay.
Yeah, so you look at the bottom of the table, and that gives you confidence level. So confidence level and then degrees of freedom, and then you see where they match up. Okay? If you wanted to, like since it's 95%, this just means that there's 2.5% in each tail. So you could associate it that way, but it's easier just to go straight for the confidence level and try and to shift back and forth. So in your calculators, if you hit second bars, and choose option 4, should be inverse T, and you can just follow along on this. It's not a too in-depth process. You don't necessarily have to try to do this right now. Hit second bars, go to option 4, inverse T. Now, area. Just like with the inverse norm, we calculate area a little bit differently. We don't just plug in 0.95. 0.95 is what's in the middle. So if I have 95% inside, I have an extra 2.5% in my tail, right? So I'm going to type in 97.5%. So for area, we would do 0.975, but now it also needs a degrees of freedom to calculate. So you would type in 11 for the degrees of freedom, and it should pop out the exact same value, 2.201. Okay with that? Okay? So, second bars, inverse T, area degrees of freedom, get your value. Or the table is much, much easier to work with on this than it is for the Z-scores. So if you want to use the table, you'll always have options for that too. Okay? So let's do the same thing, 90% confidence interval with 48 observations. So our sample size is 48. We want a 90% confidence interval. Let's do the table first. Okay? So in the table, what would we do first? All right, we'd look for 47 for degrees of freedom. So if our sample size is 48, we need 47 degrees of freedom. Now, if you look at the table on the left side, what do you notice? It doesn't have it, right? What's happening here is, at a certain point, we said that as we get bigger and bigger, our values start to become more and more normal, right? So the t-vector distribution becomes more and more normal. So at a certain point, like in the really small values, if you look from degrees of freedom 1 to degrees of freedom 2, there's a pretty big difference, right? And then from 2 to 3, there's a pretty big difference and so on. But as you progress through, that difference becomes smaller and smaller, right? So that at some point, like in this case, from 40 to 50, the differences between the individuals there would be so small that it would be almost non-existent. There's no reason to have 41, 42, 43 when they'd all be the same t-value, right? So they start to skip some values because the differences are too small for it to be worth writing down, all right? So what we do in that case, if we have a large enough sample that we don't have the exact degrees of freedom on the table, what we do is we go to the lowest value less than our degrees of freedom. So we wanted 47, we couldn't use it, so we're going to go down to 40. Never go up. The more up you go, that means you're representing a larger sample than you have, and that's not what we can do. We can only ever work back down. So if we're at degrees of freedom 47, we need to go back down to 40 and then find 90% along the bottom, and you get 1.684. Okay? So, go up to 40, go to 90%, 1.684. And that happens every time. Whatever your degrees of freedom are, if they don't show up on your table, you go up to the lowest one above. So if you had 76, you would look at 70. Now if you look, as you progress through, it starts jumping even further and further, right, eventually? So at those cases, again, you have to jump to the previous one that was the lowest. Okay? Now, on the calculator, and this is where the calculator has an advantage. The calculator has every single value stored in it. So when you want to do the calculator, you hit your second bars again, go to inverse T, and you can type in 47 degrees of freedom. It will calculate 47 degrees of freedom. Okay? So when you type in your area, for a 90% confidence level, we do 95% for area, 47 for degrees of freedom, and notice it gives us a slightly different answer. Okay? So what you need to make sure you do on your homework, on your tests, on your quizzes, when you write your T value, okay? So if you're going to do this problem, if you use the table, you would say your T star was with 40 degrees of freedom, because that's what you used from the table. Does that make sense? Your technical degrees of freedom were 47, but the table doesn't allow for that. So you would write your T star with 40 degrees of freedom. If you use your calculator, you would write out T star with 47, because you calculated exactly 47 degrees of freedom. Does that make sense? So when you're on your homework, quizzes, or tests, make sure, depending on which method you're using, you tell me exactly what degrees of freedom you used for that star or that T-star calculation. Everyone okay with that? All right. And that's it.
I don't have anything to
If you want to be more accurate, you would want to use the calculator that can use actual degrees of freedom, but if you don't care about accuracy as much, you can
We don't.
All right.
We'll do it on Sunday. Sunday next weekend.